In this video, I would like to focus on waves traveling along a stretched string, such as the guitar shown over here to the right. You can imagine when the guitar player is plucking the string, there would be a little wave that would be traveling along the string. We want to investigate the properties that affect the speed of this wave. Here I have one of my favorite apps called Wave on a String by FET. It really does a great job in demonstrating waves. What we're going to do is just change the configuration of this app a little bit, and we're going to set it from manual, which is just simply sending a wave, to pulse. And we're going to set it so that the pulse is traveling to a no end. So it's essentially what we're going to do is we're going to look at a pulse traveling along through here. You may notice that as the pulse is traveling to the right, the amplitude is slowly decreasing. That's because there's some dampening. So we're going to reduce the dampening and have it actually down to none. So you may notice that the shape of the wave is still the same and it's traveling at the same speed. Now I could change the amplitude of that wave, make it a bit bigger, and you can see that wave. You may not notice, but let's put it in slow motion. Let's send a big wave over here, and then let's send a small wave over here. And you may notice that these two waves are traveling at the same speed. I could also change the width of the wave. Let's say I have a really wide wave and send a wave over here like that. And then I'm going to have another wave that is a smaller width, maybe even smaller amplitude, and you may notice that the two waves are traveling at the same speed. So the shape of the wave at the source that's created doesn't really affect how fast that wave's going. Alright, before we jump into what affects the speed of a wave, let's just take a look again at the motion of those little beads. So you can see the beads, the little particles of that string are moving up and down, yet the wave is moving to the right. So I just want to remind you that the wave motion is said to be transverse. The particles are moving up and down, yet the wave is moving to the right. So whenever you have that kind of motion, we call that a transverse wave. Also notice that the particles do not actually move along the direction of the wave. The particles just move up and down, right? They're disturbed, but what really is transferred from one place to another is really the energy. The energy is transferred, not the actual substance. Not these actually particles are moving. They're moving up and down, but their net motion is zero. One way to calculate the speed of the wave is simply just needing a ruler and a timer. We could measure how long it takes for the wave to travel, say 5 centimeters. And so when this little bead starts to move up, then we would stop our timer. So I'm going to pause this over here, press start on our timer when the wave is created. And so you can see the wave is moving along here, and let's just stop it when it gets to that point right there. And so about 1.34 seconds is how long it takes the wave to travel 5 centimeters. And so here I have a quick little calculation. It has traveled 5 centimeters in a time of 1.34 seconds, and that gives me an answer of about 3.73 centimeters per second. Of course, I'd probably want to do this over several trials to get an average here, but that gives me a rough amount at least. Now, suppose I wanted to produce a sinusoidal wave. I want to change this now so that it oscillates, and I'm producing this kind of wave now. So this is known as a periodic wave, or you could look at it, it's kind of like simple harmonic motion that you learned earlier. You may notice that it has a certain wavelength. I'll just pause it here. If I pull up my ruler, the wavelength is the distance, say, from one crest to another crest. It's roughly about 2.5 centimeters. Well, it'd be better if you look over here. 2 waves would fit in 5 centimeters. So, yeah, we could say that the wavelength is about 2.5 centimeters. We also know the frequency that this is oscillating up and down at is 1.5 hertz. So we could actually calculate the wave speed in another way that you had learned earlier. So over here I have a little calculation showing the velocity equals frequency times wavelength. The frequency is shown here at 1.5 hertz. The wavelength is 2.5 centimeters, and that gives us an answer of 3.75 centimeters per second, which was pretty close to our previous answer. So what would happen if I changed the frequency of this wave? So I'm going to just continue oscillating this wave here and now just increase my frequency to, say, 3 hertz. What do you notice is changing here? So as the wave is moving to the right, I'll just pause it right here now. You can see that it has a different wavelength. It's kind of hard to read it about here, but you can see that if you go 5 centimeters, you have 1, 2, 3, 4 waves. What does that mean? So you can see over here I've done a little bit of calculation. The wavelength is going to be 5 centimeters divided by 4 waves. Gives me 1.25 centimeters for a wavelength. And then using the wave equation V equals F lambda, with the new frequency of 3 hertz and the new wavelength of 1.25 centimeters, I get the same speed. So that means that the frequency of the wave only affects the wavelength, yet the speed of the wave is not changing. So what are the factors that affect the speed of the wave? So it appears that changing the amplitude of the wave doesn't make the waves go any faster. Changing the frequency of the wave doesn't make the waves go any faster. What is it that affects the speed of the wave? Well, let's go back to our pulse configuration. And there's a thing that we haven't played with yet, the tension over here. You see, if I add that wave going along here, and I increase the tension in this wave, the wave goes faster. If I decrease the tension, then the wave goes slower. So it appears that tension has a relationship with the speed of the wave. Higher tensions make the wave go faster, and lower tensions make the wave go slower. So if you go back to our notes, you'll see that the speed of a wave depends on the tension. It's directly proportional to the square root of the tension, yet it's inversely proportional to the mass per unit length. This is known as the linear density. It's often written as mu. It's the mass per unit length, or you could call it the mass to length ratio. It's really essentially how heavy that string is. And if you've had any experience of playing any string instruments, you may notice that if you pluck the different types of strings, thicker strings or lighter strings, you'll find that a thinner or skinnier string will have a smaller mass per unit length. And so if you pluck that string, it'll actually have the wave go through it faster. If the string is much heavier, the wave will go slower. And that, if you've played guitar before, you'll notice that the pitch, the frequency that you hear, will change as well. Because remember that the speed of the wave is related to the frequency and the wavelength. So suppose you increase the tension of your string in your guitar, like by turning these little knobs and making it tighter, those strings, then that's going to increase the tension, which is therefore going to increase the speed of the wave. And if you're holding your fingers in the same place, which is therefore the same wavelength essentially, then you would increase the frequency. So increasing the tension increases the speed of the wave, which increases the frequency of the wave. Suppose you pluck a string that is, let's say, heavier, then that would cause the speed to decrease and cause the frequency to decrease, just kind of the opposite argument here. So the point I'm trying to say here is that the speed of the wave is, yes, indeed related to the frequency and the wavelength, but it is set by the properties of the medium. All right, so if it's a string, if it's a wave that travels in a string, then that is due to how the particles oscillate. And how those particles oscillate will depend on the tension and how heavy those particles are per amount of length that they move. One could, say, set up an experiment that could verify this equation. All you really need to do is measure the speed of the wave and see how it's related to the tension in the string. And that could be achieved by, say, maybe having a string attached to a pulley. Here's a pulley here. And then hanging off the pulley, you have a hanging mass. That mass is creating a tension in that string. That tension is really equal to mg, because the weight's pulling downwards on here. And that tension can be varied, and then you can see how fast that wave is traveling through here and how that affects it. You could also change maybe the thickness of the string and see how that affects the speed. So experiments have shown that this equation has been true. I suppose that if you look in some other more advanced textbooks, you probably could find out some proofs of showing how this is true for mechanical waves. If you kind of think of it, this is a small side note, but if you take a look at it and you look at this wave, let's go back to the animation for a second. So suppose I were to create a triangular pulse that goes along here. And if I were to just take a look at a section of this string as this pulse comes along through in here and moves, that section of that is going to start to move vertically upwards while the rest of the string is essentially horizontal. It's going to take a certain amount of time for that piece to go upwards, and it's going to depend. That piece, those little beads are going upwards, well, they're going to have a certain amount of mass. So that's why you got that mass per unit length. That depends on how much mass you have to move upwards and accelerate upwards. That's going to affect how long that pulse goes through here to the right. And also, if you think about it, there's like tension in the rope, pulling it horizontally to the right here, horizontally to the left here. Those horizontal forces are going to cancel out. But there's going to be needing some vertical part of that tension, basically pushing that particles upwards. So hopefully you can kind of see, more or less from my conceptual description, that this wave, these particles move up and down. And as they oscillate up and down, it's going to depend on how much mass there is in this segment of string per the length of it, and also the tension in the string. And that's why the speed of the wave depends on the medium, the particles at which it travels through. You'll soon see later when we get into sound waves, the sound travels at different speeds in the different media, like sound traveling in air travels at a different speed than in water, and then when it travels in, say, a solid. So they all have different speeds because they all have different configurations within that medium, and so hence the way those particles oscillate, that's going to affect how fast the speed of the particle goes. So it's not affected by the frequency, the wavelength, or the amplitude. It's affected by essentially the properties of the medium. Hopefully that helps you in solving the next problem.